Good morning. Hey, Justin, check out this haircut.
Looks nice, man.
Look at that mane. How old is that mane you got there?
This is the second generation. I cut it all off at one point like 10 years ago, and this is probably like 7.
7.
I've actually been considering getting rid of it. It's a pain in the ass more than anything, really. You know, and I always wear it in a ponytail, and it's just like, what's the point, really?
Mm-hmm. I grew a mullet out like 2 years ago because I was going to a Def Leppard and a Journey concert, and I wanted to have a real mullet. It was hard to hold that baby in there. I don't know how you do it. I lasted like 8 months without a haircut. I just let it go, and then I went into the barber and I said, just shave the sides. I want like the ugliest mullet I could possibly get. It was wonderful.
Well, yeah, there's this, especially with my hair, 'cause it's curly, but there's just like this middle ground where I just look like Bozo the Clown, and it's not cool. Like, and it lasts for several months. Like you just wear a hat, and then it kind of comes out underneath the hat, you know.
Moms pull their children close to them when you walk by. That kind of a look. Kale's with us. Excellent. Kale's with us every Thursday. All right, I give. How come I can't get a new note? All right, we have something awesome to discuss today. For some reason, I can't get a new note to show up. I wonder why that is. Let's try to close it.
Yeah, I was gonna be like, close the app. If that doesn't work, restart the iPad.
Yeah. Does that screen look different to you? I just turned it sideways. Does it look sideways now to you?
Yes.
Interesting. Okay. I should have done this a long time ago. I have a feeling this is going to look better.
Yeah, I was about to say, I think it looks better. You probably have more room to write across.
I never really noticed, but like in the videos I post for you guys, like the whole screen is super narrow and there's like a bunch of wasted space, and I was wondering if this would fill it up better. Cool. Let's see. This is a good day. You're going to be happy today, I think. So let's just launch right into it. So what we're really looking at today in 3.3 is something called the power rule, which is a badass shortcut. Pardon the French, if you're not prone to it. But it's just so cool. I don't know what else to say. But rather than just tell you what it is, I'd like you to discover it yourself. And I think I figured out a way to do this that'll allow you to see it. So what I'm going to do is start with, let's see, let's do something. Now let's start with a cubed equation. I think I'll use all plus signs just so that we don't have that distraction. So let's say I was finding the derivative of this, and we've already done this using the f of x plus h minus f of x model. But I want to do it again, and I want you to kind of think about, you know, of all the stuff that I write down and do here, what actually ends up in the actual derivative in the end. Remember how like a bunch of stuff canceled out? That's what made it really cool. So what I want you to think about is like, if I was in a hurry, like what of the stuff that I'm writing out wouldn't really have to be written down? That's what I want you to think about. So f prime of x, we say, is equal to, and I'm gonna do this in colors, x plus h cubed plus 4 times x plus h squared plus 5 times x plus h plus 8. And then, then minus f of x. And so minus the entire junk, and I'll just put it in parentheses and leave it alone for now. X cubed plus 4x squared plus 5x plus 8. All over the top of h. And technically, we want to say we want to let h go to 0. Do you have that memorized now, even by accident, that that's the definition of a derivative? That's kind of cool that you do. I think, I imagine you do by accident even. You don't need to memorize it. There'll be a note sheet on the test we take, and it'll be on there, like that formula will be sitting there for you. You don't need to memorize it. And I showed you how to, using Pascal's triangle, how to kind of multiply out x plus h squared and not screw the distributive property up. And so I'm gonna not write all that out, but just actually answer it. I'm gonna try to squeeze this all into one line. So x plus h cubed, remember the pattern to this. There's an x cubed, and then there's an x squared, and then there's an x, and then there's nothing. And then there's an h cubed, and an h squared, and an h, and then there's nothing. And then the coefficients are 1, 3, 3, 1. That's kind of cool. And then the same thing is true for the x plus h squared. But in the interest of time, I think I'll just write it out. I know it's x squared plus 2xh, but since that's being multiplied by 4, that's 8xh. And then plus h squared, but again, it's being multiplied by 4, so that's 4h squared. And then plus 5x plus 5h plus 8. And then all of this stuff in purple with a minus sign. Minus x cubed minus 4x squared minus 5x minus 8. Look at that. I turned it sideways and it worked perfectly. It fit beautifully. I'm so happy right now. So while you're processing that for a second, I'm just going to add my own note here just so that it looks awesome in your notes. This is the x plus h being cubed. This is the 4x plus h squared, and the rest is sort of obvious, although maybe I'll throw this one in real quick. That's the 5 times x plus h. And of course, this whole business is all divided by h. Now, what I want you to think about, rather than simplifying it about this, like how many terms is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 or 15 terms. I got lost count. A whole bunch of those I could have not even written down. Do you understand what I mean by that? I want you to think about what survives. There's two things that cause these terms to drop out. One of them is they have matches. In other words, there's an x cubed minus an x cubed. That caused the x cubes to drop out. But then, because later, the second thing is I'm going to write that down actually. The dropouts. One, stuff cancels, and 2, h going to 0 causes certain terms to drop out. So does it make sense? I have whatever 14 or 15 terms there. If I was in a hurry, I could have just not even written some of them down. You understand that? Like what things, I just want to try to give you time to process this. You guys chime in a little bit. Like what, you tell me what things are going to cancel out that in a sense I wouldn't even had to write down.
Anything with an X terminate, right?
Yeah. Remember what happens here that's amazing is all the non-H terms go away. In other words, like this entire stuff right here, I could have just not even written it down because x cubed and minus x cubed plus 4x squared minus 4x squared plus 5x minus 5x plus 8 minus 8. Does that make sense? I crossed it out a little too vigorously. I want you to be able to see it later. So does it make sense I could have just not even written those down? Secondly, let's switch to purple. What stuff is going to end up, what other things could I have not written down simply because there's going to be H's left and then H is going to go to 0, so I could have just not written those down too. Do you understand what I mean by that? Like, give me some examples. What am I looking for?
Like, I mean, anything with H in it would go to 0.
After, don't forget we have to divide by H. So after dividing by H, it goes to 0.
So anything with H to a single power, that term would remain.
Yeah.
With H to a higher power would drop 1 power, and then H would go to 0, so then the whole term would be gone. Right?
Correct. Only H's with a kind of a single power is the word Logan used. Those are the only ones that sort of survive. Do you understand what I mean by that? In other words, isn't H cubed divided by H is going to be H squared, and there'll be an H squared left, and so that's going to be gone, and I could have left that out. Does that make sense? Or this 4H squared divided by H is 4H. 4H will go to 0. So anything that's not just H is going to go away. So this H squared is going to go away. So how many terms survive those two dropout schedules, like stuff that's scheduled to drop out? Do you see them all? I think Logan said 2. I don't know how many there are. I got to go find them. So here's one. That one survives, right? And this 8xh survives. Is that it? No, there's one more. That's it. In a sense, if I was in a hurry, really that's the only 3 terms that are going to end up in the answer. You understand what I mean? Again, this is what mathematicians do. They just look for patterns. They look for shortcuts. And so in the end, you could actually say f prime of x then is going to be 3x squared, because this h will cancel and there won't be any h's. So when h goes to 0, that term survives, right? And the 8xh, its h cancels as well. And so you just get an 8x. And then the 5h, the h cancels, and then you just get the 5. Like of the 14 terms, if I counted right, only 3 of them actually end up in the answer. And so what we want to do today is kind of try to, if you will, look at our original problem up here and sort of get a little faster at this. Like don't write every single term out. Like, can we somehow skip over all of that and just kind of get down sort of straight to here a little more quickly? So those terms survived, if you will. So
I think I might have figured it out.
Tell us. I'm tempted to say tell us, but I actually would like to hear what you have to say. So go ahead and do it. What do you think you see?
I thought I saw this the other day too, and it worked here. it's basically just multiply each term by its exponent. If you bring the exponent down in front of each term and multiply it, and then after you do that, you would add the exponents, like a 2, and then a 1, like decreasing from the first term down.
So in other words, what he's saying is, what Zamar is saying is like this 3 up here, if you will, ended up down front. And then it was a 3, and then it got reduced to a 2. This 2 ended up down front, and that turned into an 8. And then this became x to the first. And so that's what Zamar is sort of positing. Well, not to rush into this. Let's do one more, and let's even do it. Let's even make it worse. Let's try. Let's try f of x equals x to the 4th, which is just horrible, plus 2x cubed plus 7x squared plus 5x plus 6. Again, I'm using all plus signs just so we don't have to like worry about getting rid of like losing it with negative signs. And so let's see what happens if I do the same thing. Now, this is not going to make it in one line anymore, but again, watch how I'm able to write this out. So first of all, we know the derivative is x plus h gets replaced with x. So we have an x plus h to the 4th, and then we have 2 times x plus h cubed, and then we have 7 times x plus h squared, and then 5 times x plus h. That won't do. And then plus 5. And then minus, I'll just write f of x because I'm going to run out of room. Remember how that's going to go away anyway? It's going to go away anyway. So
plus 6 on the end.
And then all divided by h. So let's multiply this out. So x plus h to the 4th. Whew, I got to be careful here. So there's an x to the 4th, and then an x to the 3rd, and then an x to the 2nd, and then an x to the 1st, and then nothing. And then there's an h to the 4th, an h to the 3rd, an h to the 2nd, an h, and then nothing. And then the coefficients from Pascal's triangle, I showed you this quickly the other day, would be 1, 4, 6, 4, 1. Now, again, what I would like for you to do is just be paying attention to, because notice there's just a lot of terms. This is going to take a lot of terms, but most of these are going to drop out. So this is the x plus h to the 4th. Now we got the x plus h to the 3rd. Let's go tackle that one. So I'll have to do this later, I guess, because I don't want to get confused. So it's 2 times and then x plus h cubed. And we saw that a second ago. It was x cubed plus 3x squared h plus 3xh squared plus h cubed. And so that's our 2 times x plus h cubed. And then I think I'll squeeze 7 in here. I think I can squeeze it in. 7 times x plus h squared. That's 7 times x squared plus 2xh plus h squared. And then I think I'll just squeeze, you can recognize that, so I won't label it. And I think I'll just squeeze the rest of that in down here at the bottom. In other words, plus 5x plus 5h plus, I said plus 5, but it was plus 6, right? Why didn't you guys tell me I was dumb and got that wrong? I put plus 5 here, but that was really a 6 in the original problem, right? And again, it's sort of still, it's still minus f of x, all those terms. But remember, those are going to go away anyway. So it's like, I'm trying to speed this up. And of course, it's still all divided by h. But let's write out now, because I still have to multiply some stuff out. Let's write out the whole thing completely multiplied out. So really all I have to do is distribute. I have to distribute this 2 because I just wasn't sort of smart enough to do it all at one time and distribute that 7. That's really all I need to do here. So I have, and I'm going to try to write this really small so it all fits in one line. So I have x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed. Again, you're looking at this saying, you're thinking right now, which terms, like there's terms I don't even have to write down right now because we know they're going to go away, right? Just be thinking about that. Plus 2 times all of those green terms. So 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed. And then kind of all the rest of the terms plus 7x squared plus 14xh plus 7h squared. Darn, I didn't quite make it. Plus 5x plus 5h plus 6, all minus f of x, and all over the top of h. I wish I could have squeezed that in one line. But this time, what I would like you to do is just stare at this and think, not so much let's cross out the terms that aren't going to survive, but let's actually just put a box around the ones that are going to survive. I'm not going to even cross stuff out. I'm just going to box stuff that survives. What Logan said last time is true. What survives? There's only one thing to look at here. What are you looking at? What are you looking for? For things that survive, what are you looking for?
Things with an H term.
1h. That's it. If it's got 1h, it survives. So this survives. H squared, nope. H cubed, nope. H to the 4th, nope. 2x cubed. 2x cubed doesn't survive because I'll be subtracting it from this f of x over here. It's gone. This term survives. Then there's an h squared, nope. H cubed, nope. 7x squared, nope. 14xh survives. And 5h survives. What I'd like you to notice is, where are all of those terms? There's 4 of them, and where are they? Like, look at the red ones. Where is it in the red ones? Where is it in the green ones? What'd you say, Alden?
The second term of each of those.
It's the second term in. The second term in, based on the pattern that we saw with Pascal's triangle, it's the second term in that's going to have an H every single time. So again, if I'm in a hurry, then I could say that f prime of x after cancellation, after cancels and h goes to zeros, is going to be 4x cubed, and then plus 6x squared, and then plus 14x, and then plus 5. Do you agree with that? Because remember, the h's cancel. That h on the bottom cancels. That's why we're looking for 1h. What I want you to think about is the process of speeding this up. I mean, I really don't need to multiply everything out. I just need the second term of each one of those expansions. I need the second term only.
Where does the x to the 4th cancel out?
Good question. Somebody answer that. Where does the x to the 4th cancel out?
Minus f of x.
Yeah, remember the f of x is minus.
Ah, right. Yep.
Thank you for asking that. Minus x to the 4th minus 2x cubed minus 7x squared and so forth. So all the non-h terms drop out every time. It's the second term in every time that just has an h in it. The question is, do you see it? Do you see how it got there, if you will? What's happening kind of every time? Well, the second term in will always have, it's kind of like if this is to the fourth power up here, then the second term in will always have a 4 right here because of Pascal's triangle. If it's a cube term, then it'll always have a 3. Now, in this problem, we ended up needing then to multiply it by 2, which is why it became a 6. The squared term, x being squared, will always have a 2. So do you see what I'm highlighting here? Like that 4 showed up because of this 4. That 3 showed up because of this 3. That 2, the second one in, that 2 showed up because of this 2. And to Zamar's point, notice the effect that has is, well, the first term goes away every time. Well, think about what the first term was. If this first term was an x to the fourth, then the first term was an x to the fourth, but it went away because it got canceled out. And then so the next term in is always 1 degree lower. Does that make sense? The term that survives is always 1 degree lower, but then none of the rest of them do. And then secondly, this 3, if you will, ends up kind of multiplied down front, which is why that ended up being a 6. And so Zamar was actually onto it. He's right about that. The question is, do you see it?
So
Yeah, simple the power rule actually is.
it kind of looks to me like you're reducing like the overall power of the equation by 1 because you're starting with x cubed instead of x to the fourth. And then you're multiplying the lead coefficient by the power effectively to get it. Because the lead coefficient of the cube term was 2 and the power was 3, which gave us the 6x squared. And then the lead coefficient was 7 squared, which gave us our 14x. And then plus 5 was remainder with no coefficient. Just something that I see.
Yeah, let's look at that. So let's just take a look at the pattern that let's just take a look at the last 2 problems, and I'm just going to try to write them all out so you can see them real good. Again, I just wanted, I'm not wasting time here. I'm actually just trying to give you time to process this. So here's where we started with f of x, and then we turned it into this. The question is, can you see the pattern, just to go straight to it and not have to do any of this anymore? I'm guessing some of you see it. I'm going to go back and actually copy the original problem down too, just so you can see it next to it as well. So here was our first problem. And then we got what for its solution? We got this. So collectively, this was our first example, and this was our second example. question is, do you see the power rule?
I think this is fantastic.
You should think it's fantastic. This
I
is
do.
amazing. Like, this is the second part. The fact that you can find the exact slope at any point when that should be impossible, because you just let 2 points get infinitely close, and so we're actually getting the exact slope. And now, to top it off, if that wasn't cool enough, you can actually just go straight from the function to its derivative. This is the first of about 5 or 6 shortcuts I'm going to show you, because every one of them, you can find the slope at any point unless it's a cusp or some weird, anomaly. Exactly. But the second is there's a shortcut for everything. Every function has a shortcut. This is the easiest one you can appreciate. If you're going to start showing people shortcuts or show them something, it's like, this is the easiest one you got to see.
It's too bad I understand this. I don't understand the rest of it. So
So the question is, if I give you, here's your little kind of test, and I just want you to try this on your own. If I gave you something like this now, like 4x to the 5th minus 7, I'll skip the 4th power and just go, I don't know, to the 3rd, and then plus 9x squared plus 3x minus 7. Like, can you just write down the derivative now? And not everybody sees this yet. Don't get me wrong. I didn't even, a few of you kind of said a few things, but probably you didn't understand the language that the person used to describe this. But if you think you see it, go ahead and take a stab at it. Try it.
20x to the 4th minus 21x squared plus 18x plus 3.
That's what I got.
That's what I got.
That's what I
Yeah, me
got.
too.
Me too.
Nice. So are you seeing the pattern? Like, to make sure everybody sees it, you're taking this number and multiplying it by that number. And then you take the exponent, which was x to the 5th, and you decrease it by 1. It drops down a power. You take this 3 and you multiply it by 7 so that becomes 21. And then you take x to the 3rd and you drop it by a power. You take 2 times 9, which is 18, and you take x to the 2nd and you drop it by a power. You don't have to write the 1 there, of course, but that's cool. Now, what do you do with the x? I'd consider, you probably thought of this as like the x just disappears, but is it any different? Isn't x to the 1st? And so you say 1 times 3 is 3. And then if you decrease the power, what does the power become?
1.
Becomes not 1.
Well,
It becomes 0, which makes it equal
One.
to 1.
Yeah, but
Equal.
it's next to the 0, 1. So that last one isn't different. Do you understand that? It's actually the same pattern. So you could just think it disappears. Now I'm going to erase this, but think about this really quick because it's just interesting. Because I kind of asked you this yesterday. If I gave you the line y equals, say, 2x plus 7, notice that's a straight line, which means no matter where you are on that, the slope is always what?
2.
Slope is 2, right? You've memorized before you got to this class that number is the slope right there. Does that fit the pattern that we just described?
Yes, it does.
That's a polynomial too, isn't it? Y equals 2x plus 7 is just the tail end. It's just that part of it right there, isn't it? So what we've looked at here is actually a pattern that just blows up to the next level. You never thought about that before. You just, like your math teacher told you the number in front of the x was the slope and you went, okay, and just memorized it and did it. But it's like, this is a part of deep magic. This is a part of a pattern that actually continues. So you just thought the number in front of the x was the slope, but actually it was the power rule. You take 1 times 2 and decrease the power of the x by 1. That's how you get it. And then that pattern actually works for x squared and x cubed, next to the 4th, next to the 5th, and next to the 19th, and next to the 37th, and any number beyond that. That's the power rule. Now, I don't know about you, but I kind of hate textbooks, because if you read this section, I don't know what they did to get this idea across to you, but I bet it was kind of hard to understand. Well, in defense of people writing math books, how would you put this into words? If you had to write a sentence or two how would you put what you just saw into words? The concept is actually really simple. As long as a person can multiply and subtract, they could actually take a derivative now. Does that make sense? If you have your multiplication tables memorized, like a fifth grader has their multiplication tables memorized, you could actually teach a fifth grader to do this. Now they wouldn't understand what they were doing, and they wouldn't understand the theory and all the, you know, Pascal's triangle and how to expand all this stuff, and, you know, why f of x plus h minus f of x is really cool and all that. They wouldn't understand any of that stuff. But in terms of what you're actually doing, it's actually fairly straightforward. But to write it down, you know, you're going to say things like, take this number and multiply it by that number, and then take this number and subtract 1 from it. It just sounds like gibberish. But what you'll see in the book then, to kind of, I don't know, conceptualize this, is if f of x, oops, that's not true. And you can appreciate, why can't I erase you? You can appreciate why somebody would call this the power rule, I bet, because aren't these powers, like to the fourth, to the fifth, those are powers, right? And I could also see it being called the exponent rule. If you were to make this up, you might come up with your own name. The power rule then says if you have some function that has, say, an x to the, and of course what they're going to do is not use numbers. They're going to say, you know, x to some power, like a or n or something like that. X to some power. Well, you tell me, what would the formula be? What do you do to whatever number's up there? You just did it to 4 and to 3 and to 5. You did it to a whole bunch of numbers. Well, you know, describe what you just did. If it's any number, like this is what mathematicians do. They try to write down the formula. Well, there's a 1 out in front. So when you bring the n down, you multiply it by what's in front. And then it's now times x to what power?
N minus 1.
Yeah, take 1 away from it, n minus 1, in a sense. That, my friends, is the power rule. Now, again, I am going to ask you for sure on our first test to do this the long way, but you should never get it wrong now. If I give you, and I won't give you something huge, a cubed equation, you're probably going to make some kind of a silly math mistake, right? That first cubed equation we did, that takes a lot to kind of expand all that and not choke. But I will ask you for a squared equation. Like, in other words, when I mean ask, I mean f of x plus h minus f of x. In other words, don't forget, although we are now entering the world of shortcuts for the next 8 weeks, 9 weeks, and saying, let's try to figure out how to take the derivative of everything. And, you know, how does this work with logarithm, and how does it work with tangent and all these different functions? And we're looking for shortcuts and so forth. Don't forget, this is just a technique to find the slope. And you can see that when you do f of x plus h minus f of x over h as h goes to 0, you can see the slope in that. But we just realized, oh my God, there's a pattern to this because of the deep magic and beauty of math that keeps us, we don't even have to write all that stuff down, but that is where it comes from. And you just got to understand, in a sense, you just got lucky. You see what I'm saying? Like as a human being, it's like we decided we think a derivative is worth taking. We want to find the slope. And we just got extremely lucky that we don't actually have to do that all the time. We can just write that out. Oh my God, that's amazing. That's what you should be thinking right now.
Does our shortcut work for negative exponents and fractional exponents, like square roots?
So Logan asked a good question, like, you know, how far reaching is this? So let's I couldn't have paid you anymore to ask that question, because that's where we need to go next, which is, in a sense, now you know how to take the derivative of a polynomial expression really quickly and really easily now. But what about some of the other stuff we did? Like, for instance, let's try this. Again, I'm going to try to make this really simple. Instead of, you know, 2x minus 3, but didn't we look at radical? We looked at radical expressions. And so let's see if we can go find a shortcut for that. Now, first, let's do that the long way. F prime of x would be equal to f of x plus h minus f of x all over h as h goes to 0. Notice I'm being lazy. I didn't say the limit as h goes to 0. I'm just being lazy, but at least I wrote it down. I'm not that lazy. I want to let h be 0. And so then we said yesterday, we said to get out of this mess, there's no way out of this mess unless you amazingly multiply by the conjugate, right? And you can do that as long as you do it top and bottom, because effectively then you've just multiplied by 1. And so you're changing the way it looks without actually changing what it is, right? Change the way it looks without changing what it actually means. So we saw from yesterday then that when I multiply this by this, I'll get 3 times 3, which is 9, and I'll get the square root of x plus h times the square root of x plus h, which actually gets rid of the square root.
Wait, but since that's a cube root, that's not how they, since it's not 3 times the, oh,
Yeah.
you're right.
Yeah,
We were doing the other one.
you break up a little bit when you're talking because of your mic or something, Logan. But Logan asked the question, like, what if it was a cube root? That's another question here. Like, what would I be multiplying by to get rid of a cube root? We might talk about that. That's a good question. And then does it make sense that when I multiply this by this, I end up with 9 times the square root of x times the square root of x plus h, but then when I multiply this, don't I end up with the same exact thing but a minus sign? Again, the conjugate gets rid of the 2 middle terms, and that's why this is so cool. So those 2 middle terms drop out, and then the last thing I have is just -3 times +3 square root of x times the square root of x. That's what I end up with on top. And then on the bottom, I just have everything that I have, which is an h times the expression. And notice I put parentheses here. Why is it important to put parentheses there?
Because there's 2 terms that it's being applied to or multiplied against.
If you write it like that, we know what you mean, but you just screwed up the distributive law. It's h times all of that junk, and because of the plus sign. And again, what did we observe that's really beautiful yesterday? We observed, hey, when you multiply this out, you end up with 9x plus 9h minus 9x. And again, the amazing thing about calculus is the x terms, just like they did a minute ago, go away. And so you end up with just 9h up there over h times our expression. Which means you can now say that the h's drop out. And so you're very excited now because you're like, oh my God, now I can let h be 0. This is so exciting. And so you finally say then that f prime of x, so I'll say now h can be 0, which means that term goes away. And so now you just have a 9 on top, and you have 3 square root of x plus 3 square root of x, which is 6 square root of x. On the bottom, which I guess reduces, maybe I'll reduce it to divide the top by 3, divide the bottom by 3. You get this. And so the same question remains, which is there something we could do to jump straight over all this algebra? And the amazing thing about calculus is the answer is yes. So we need a new rule. Well, I want you to think about that. Let me write that a little differently. Would you agree that f of x could also be written as 3 times x to the what power?
1/2 power.
1/2 power. I want you to stare at that for a second. Our answer came out, well, how would you write that with exponents? Let's see, isn't that 3/2 times x to the 1/2, but x to the 1/2 is on the bottom, right? What does that mean? If that down there is x to the 1/2, but it's on the bottom, how do I write it if I want to move it up to the top, up to the numerator?
-1/2.
To the second?
-1/2. Stare at that for a second. What's the shortcut?
Multiply the square root power to the what's inside the square root box, or the denominator power to the variable, and then
Yeah.
times the numerator or the constant by the numerator power.
Is this any different than the power rule we just saw a minute ago? It is not. Like, this is the same exact rule. You're telling me that the power rule works even if the powers are not whole numbers? Like, again, we didn't start this problem by thinking of 3 square root of x as 3x to the 1/2 power, but the power rule works even if the powers are fractions. You got to be kidding me. That's amazing. You should have like a chill going down your spine, like, what a universe I live in. I can't believe it. So the power rule still works. Like, we don't need a new rule for this. In a sense, I don't know if you ever thought about this, but there's no such thing as a square root. Like, you don't need square roots and cube roots. You could write those with fractional exponents. And your life in algebra would have been far less painful if nobody ever invented that stupid symbol and just said, there's no such thing as a square root of x, it's just x to the 1/2 power.
All right, so my only question is, I get that the 1/2 was on the bottom, so it's negative, but technically, do we reduce the power? That's what's kind of confusing me right now.
Yeah, well, think about what you did. If you take the power and multiply it by 3, 1/2 times 3 is 3/2. And then what do? What did we say the power rule said to do to that exponent?
Subtract 1.
Subtract 1. What's 1/2 minus 1?
I see.
Negative 1/2. Still works. Oh my God. So that means if you had a cube root, you could use the same strategy then, right? Let's just try this then. What about a cube root? In other words, what if the equation was f of x equals, I don't know, let's just make up something like 3 times the, no, let's not use 3 because cube roots already have 3 in them someplace. So let's make it 4 times the cube root of x or something like that. Well, if you say, hey, I know how to write that, that's 4 times x to the 1/3. And now I'll just use the power rule. I don't have to do this conjugate stuff. You can. I can just use the power rule and I can immediately write the answer down. Let's see, what does the power rule say? It says take this 1/3 and multiply it by 4, so that becomes 4/3. And then 1/3 minus 1 would be negative 2/3. So done. What? From yesterday, I just want to graph both of these really quick and, kind of check my work, if you will, and kind of see, let's just look at both of those graphs and see what we get.
All right, so I have a question that relates to that. So say we had an equation that was like I ran into an equation the other day that was 9/x. How would we use this for that?
Good question. We'll tackle that. You are also reading my mind because that's exactly where we need to go next. So I'd say I could probably find a cube root button on here, but I don't see it immediately. So I'm just going to type 4x to the 1/3 power. So there's the graph of that. And notice it's undefined, like, because I showed you this graph going out the door yesterday, as it turned out. It's like the slope at 0 doesn't work. And we're saying that we think we just found the derivative, which I'll call g of x. I just want to know, can you stare at this graph and go, yeah, that kind of looks like it's right to me. Before I graph it, can you stare at this and see different slopes? Like out at 5, the slope is maybe 2/3 or something like that. No, I didn't want to do this, but I guess I'm going to do it really quick. Let's see. Okay. I want to put a point that slides along because I want you to be able to look at the same, I want you to be able to look at what I'm asking you to look at. So f of a, dunk. And of course it says add a slider because it's saying I can't graph that. There's no such thing as math with letters. So what would you say the slope is right there? Like I'm at 1, I'm at x is 1. What do you think the slope looks like right there? Just guessing.
Like 1?
Yeah, like maybe 1. And then what's the slope do as you go out here? It's getting what?
Slope's decreasing. It's like out there, maybe like
Decreasing
1.5 or
but staying
1/3.
positive, right? It's decreasing but staying positive out here. And then what's the slope right down in here? What does it do when I go this way? Isn't it getting what? What's the slope like right there?
Like 10,
Big,
maybe?
right? Big positive. And then when I get over here, notice it actually stays positive. It's still positive 10, and then it gets smaller again. So the slope is always positive. It's really big right in here, and then it just gets smaller and smaller and smaller. Well, that means the y prime graph is all going to be above the y-axis, right? And I'm going to get really big numbers around 0, and then small numbers out from there. So the question is, if I go in here and graph our answer, which we said was 4 divided by 3 times x raised to the -2/3. The question is, does that look like it should from yesterday? Yeah, look at that. See the blue graph? It's saying if you're right around 0, you get really big numbers. And notice it's symmetrical. Like the red graph seems to be symmetrical. When you get away from 0, you get small positive numbers. So from yesterday, it's kind of like, wow, I guess the power rule does still work here. Do you see what I'm saying? I just kind of use this to check my work. In a sense, that's yesterday's knowledge doing its job, if you will. So it's like, oh, that's cool. So in case you decide you want to play with this, I'm just going to take 2 seconds and throw it into the notes here. And I'll just write us this note here, say, seems to be true. Seems that the power rule is working here. So Andrew said, I just have one question, but then he asked another question like 60 seconds later. I go, what kind of, did you lie to me?
A multifaceted question, okay?
But then
multiple parts, A, B, and C.
you can ride that for the rest of the term. I just have one question. It's a math question.
Has 26 parts. That way, if I run out of parts, I can add subparts.
Exactly. You can ride that. You can ride that mule. So didn't we also look at fractional equations yesterday? That was like our third type. We looked at radical equations and we said, oh, if you multiply by the conjugate, you can get out of that mess. And then we looked at fractional equations and we said, hey, we can get rid of all the junk in the fractional equation. And, you know, so it was something like this. So I'll make it a little more interesting. And again, let's quickly do this the slow way. So f prime of x would be equal to f of x plus h minus f of x all over h. And we want to let h go to 0. And so then we say, okay, cool. We got ourselves out of this mess by multiplying both sides by one denominator and then the other denominator, right? Isn't that how we got out of this mess? So we're going to multiply top and bottom by x and x plus h. So this x plus h will cancel this one, and this x will cancel this one. And so what I end up with then is when I multiply x times 4, this x will kind of survive that 4, and this x plus h will survive that 4. And so I end up with this all over my denominator, which is h times x plus h. Is that too fast? Did I go too fast there? And again, you might be tempted to say, you know, something dumb like, I'm going to cancel those two things out, but you'd be violating the distributive law, and so you aren't going to do that. But what happens here, as we said, as we saw yesterday, is beautiful things, which is you end up with 4x minus 4x minus 4h. And again, magically, amazingly, the 4x's cancel out, and so this just becomes minus 4h over h times x plus h. And now we can let the h's cancel, and so we're free to let h be 0. And so you would say that the derivative then, if you're all done, is minus 4 over, letting h be 0, 4 over x times x, or 4 over x squared. The question is, that's the power still. Isn't 4 over x the same as 4 times x to what power? If I wanted the x to be up on top?
Is it 2 over 1?
What do you, right now this power is 1, it's 4 over x, which is 4 over x to the 1. So if I decide I don't want this to look like a fraction.
-1?
-1. My guess is half of you would answer yes to this question, but I'm going to make you answer it. How many people would like me to quickly remind you, like, why is that true? Because right now I'm just saying, I'm saying something like you can move it to the top and change the sign, and that's okay to do. Thank you, Faith, for being brave. A couple of you nodded your heads. So I'll tackle that in just I'll tackle that right now really quick. Here's the little side note. Again, this falls into the category of things that you should know, but if you didn't look at it deeply, and then frankly, I don't know about you, but I have to see everything twice to understand it. Once is not enough. Like every book I read, I got to read twice. If I actually want to understand it, it just goes away. I mean, it just doesn't give me enough time to process. The way I say it in like a class like this is soak. You need to have time to soak and just kind of take this in on your own. Me saying it doesn't mean you instantly understand it. Here's a brief review of how exponents work. If you have 5 x's on top and 2 on the bottom, that's super simple. You say x to the 5th means, well, 5 x's multiplied together. X to the 2nd means 2 x's multiplied together. And so then you say, well, this x divided by this x is 1, so I can get rid of that. And this x divided by this x is 1, and so I can get rid of that. And so I say the answer to that is x to the 3rd. And then you sort of say, well, hey, I see a pattern there, which is every x on the bottom cancels with 1 on the top. So if there's 2 of them on the bottom, then that'll cancel 2 of them on the top. And so, hey, I could subtract. I could go 5 minus 2, and that's like the shortcut, right? But if you don't understand that shortcut, then you forget it and mix it all up. So what if you then had something like x to the 6th? No. What if you had more x's on the bottom than you had on the top? Well, it's no different, is it? Logic. 4 x's on the top means 4 x's on the top. 6 x's on the bottom means 6 x's on the bottom. So you do the same thing. You say gone, 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 gone. What does that leave? 2 x's on the bottom, right? But what if you use your cool little shortcut rule where you go, you know, over here we went, hey, x would be to the 5 minus 2. What do you do? What happens if you do that over here? Don't you get x to the 4 minus 6, which is actually -2? What that's telling you is 1 over x squared is equal to x to the -2. X to the -2 doesn't make any sense. Do you understand that? If somebody says, what's 5 to the -2 power, you should say, that makes no sense. Like, how do you take 5 times itself negative times? It doesn't make any sense. What you have to say is, oh, what that means is 1 over 5 to the 2nd. Exponents that are positive make sense. Oh, that's 25, so it's 1 over 25. That's what a negative exponent means. What's the long and the short of it? That means you can move it from the bottom, x squared, to the top and change the sign to something negative as a shortcut, as a result of how exponents work. So that's what we're doing here. Brief refresher. So if that's true, then how could you rewrite this final answer down here? Instead of 4, negative 4 over x squared, how could you rewrite that if you wanted to? Well, negative 4 is there, but then that'd be x to what power?
-2.
Negative 2. So does the power rule still work?
Yes.
-1 times 4 becomes -4. And then x to the -1, what do you do to the exponent?
Subtract 1.
Subtract 1. -1 minus 1 is -2. Oh my God, the power rule still works. So the power rule is well, powerful. It doesn't matter what the exponent is. It's nice if it's positive, like x to the 4th, but it can be negative and it can be a decimal or a fraction, still works. Any power works. Unbelievable. This solves a lot of problems. So the power rule is powerful. Little side note, how powers work. The power rule is powerful. Let me show you just some examples. So this is kind of the kind of thing you're going to see in the book. Then you might see something like this. 15 15x to the 4th plus 12x squared. I don't know why I'm looking at my notes. This is kind of just a random problem anyway, but -9. But what if that's not the only problem? What if it's all over 3x squared? What if you have a giant fraction like this? Well, what we've noticed, and there's some deep magic here we'll get to later on, is in a sense what we've noticed back here is that derivatives don't mind plus signs. In other words, this problem back here, we actually kind of looked at each of these separately. We said x cubed, there's its answer, and then the plus sign just kind of came down for the ride. In other words, we got to just look at each term separately. And unfortunately, it turns out that division isn't quite that simple. So for now, think of it as like derivatives like plus signs. But does it make sense that you could actually, well, isn't all 4 of those terms up there are all divided by 3x squared. So couldn't you go 15 divided by 3 is 5, and x to the 4th divided by x squared, that 2 of those would cancel and it'd become 5x squared. What's 12x squared divided by 3x squared? You tell me.
4.
Yeah, just 4. What's 6x divided by 3x squared? Well, 6 divided by 3 is 2, but what's x divided by x squared?
X to the -1.
X to the -1. And do you see why I want to write it this way? I don't want to write stuff as fractions. I don't want to write stuff as radicals. I want to write it as x to a power. If that power is a fraction or it's negative, fine. But I just want to write it without fractions. And then what's the last one? What's -9 divided by 3 is -3. But how do I write x squared if I don't want it on the bottom? Somebody help us.
-2.
Yeah, it's an x squared on the bottom or an x to the -2 if I move it up on top. Do you notice now it is sitting there in such a way that I can actually just apply the power rule? So that's what f of x is equal to. But now I'm actually able to find f prime of x really easy. The 2 gets multiplied by the 5, the x gets reduced by 1. What about 4? What's the derivative of a constant? What's the derivative of 4?
0.
Take a quick look at the graph. Would you agree that's the equation y equals 4? Remember,
Yes.
to graph y equals 4, you don't memorize. Was that a horizontal or vertical line, you just think, well, graph all the points where y is 4. X is 1, y is 4, x is 2, y is 4, x is negative 90, y is 4, x is 15, y is 4. I get a horizontal line. What's the slope of that line?
0.
It's 0. So the derivative of a constant is always 0, but it's not because you need to memorize that. It's because, well, what's the slope of y equals 4? It's 0. So I'm going to write the 0 in here. What's the derivative of 2x to the negative 1? Well, I take negative 1 times 2. And then what do I do to that exponent? What's the power rule? I take negative 1 and do what to it?
-1.
Subtract 1. The last one, I take negative 2 times negative 3 and I get positive 6. And again, lots of you are going to screw up right there, right? That's an easy mistake to make. What's negative 2 minus 1?
-3.
Negative 3. So, and I'll just note this, but if I'm going to erase this, but if I said the equation was y equals not, you know, like 1 over x, but 1 over x cubed, like we never even tackled that. We didn't look at a graph like that. We just had the x term on the bottom, but the point is the power rule tackles them all. So in other words, boom, power rule. Boom, power rule, done. Didn't have to write anything out, think about conjugates, think about fractions, any of that stuff. I can just use the power rule. If I can write it as junk plus junk plus junk plus junk with no fractions, no radical signs, if I can clean up whatever mess I'm given, no problem. Amazing. So
would this be
is the
okay?
kind of example questions that you're going to get in your assignment. Go ahead.
So like this would be an acceptable way to write it, right? Like for a test or something with the
Yep.
negative exponents.
Yep.
We could
Now,
also.
of course, your online homework may say something like write it without negative exponents. And so you should say, you know, while you're pissed off, fine, I can write it without negative exponents. If somebody makes me. And of course, I'd say there's an argument for that, but because I don't know about you, but I sort of find myself understanding positive exponents. And so I like the look of that purple version of the answer better. But as far as I'm concerned, you should be able to do that. Like anytime if somebody says reduce it, write it in simplest form, fine, I can do it. But it's not like that added anything.
I feel like I'm inclined to disagree with you about that purple form. I actually don't mind negative exponents as long as it's all in one line.
Yeah. That's my point, is like you should be able to write it either way. But there's advantages to both, right? The second one, the purple one, is no negative exponents. I like that, but I hate fractions, and you know the red answer didn't have fractions in it, and so that's a matter of personal taste. My answer, my attitude is as a teacher when you take a test is, if I want the answer in some form, I need to tell you that. It's not like I can say wrong, you know. It's like you should have simplified it. Those are both right, and I don't care is my answer. But if some online homework system cares, you should be more than capable of messing with that. Fine, I can answer it the way you want it. What about this? Another example. We're not going to get as far as I wanted to get today. Here's an even uglier question. What if I told you f of x was equal to 4x to the 2/5 power minus 5 over x square root of x plus 2 over x cubed? You should be able to say, I got to go fast here, that, okay, fine, I'm already happy with 4x to the 2/5. It's sitting there without a fraction in it. What is x times the square root of x, though? Well, isn't x times the square root of x, x times x to the 1/2, x to the 1 times x to the 1/2. And what do you do with exponents when they're multiplied like that? Quick
Add them
review.
together, right?
If you have x squared times x to the 3rd, doesn't that mean x times x times x times x times x? Oh, x to the 5th. Oh, I just reminded myself, you add them. So that minus 5 would be 5 times, well, it would be x to the 3/2, because you add 1 plus a half and get 3/2, but it's on the bottom, so I would actually have to move it up and it'd be negative 3/2. Does it make sense? I don't want to write this as 1.5 if it's a little nicer to write it as just one fraction rather than mixed fractions. So it would be x to the 3/2, except for it's in the denominator. So to move it up, it's got to be negative. And then the last one isn't quite so bad because I would just move it up and it'd be x to the -3. And so now it's in a form where I can just use the power rule. Isn't that amazing? So it's really easy then to say what f prime of x is. I take 2/5 times 2, that'd be 8/5. I guess I can't reduce that. And what's 2/5 minus 1? Should be able to do that in your head. 2/5 minus 5/5 is -3/5. And then -3/2 times 5 would be positive 15/2. What's -3/2? Take away 1.
-5/2.
-3/2 minus 1 would be -3/2 minus 2/2, which would be -5/2. And then the last one, -3 times 2 would be -6. If I take 1 away from -3, now it's down to -4. Done. Like, I'm personally quitting right there unless somebody makes me answer it differently. I'm done. That's pretty cool. I got to show you one more example. God, there's something we needed to get to that we're not going to get to, and I don't even know what to do. One last example. What would you do with this? That's like a power to a power. We'll elaborate on this a little bit more later on, but does it make sense you could just, well, doesn't that squared, like, can't you also work that out? In other words, squared means 2x plus 5 times 2x plus 5, which is 4x squared plus 10x plus 10x plus 25. Does it make sense that, you know, maybe is there some way that I could do this without multiplying it out? And of course I'd be, you know, if this was a 12, that'd be not good. Like, oh my God, I got to multiply that out. Is there some way to deal with it without having to multiply it out? That's a question for a later day, but at very least for now, couldn't I just multiply this out? And now it's a parabola. And then, oh, okay, now the derivative is really easy. That's a really simple power rule. 2 times 4 would be 8. X to the second becomes x to the first. 1 times 20 is 20, and then that'd be x to the 0, and then the derivative of a constant, the derivative of 25 is nothing. Again, you tend to not write the 1 there, but it's like, there's the derivative. Apparently the derivative of 2x plus 5 to the second power is 8x plus 20. True. So the point is, you got to write it, you got to get rid of fractions and powers, and in this section there's a lot of derivatives you can take because of the power rule. You can get rid of radical signs, you can get rid of fractions by just writing them as exponents. That's an amazingly powerful concept.
Can't you just effectively multiply the inside of the parentheses by 4?
Yeah, so what you're thinking of is shortcuts, right? Is there some way I could have skipped that step? And we'll save that for another day because that turns out to be fairly complicated. But we can tackle a lot of problems now because of the power rule. That's amazing. Now, I got to show you one last thing that's amazing. This is in your assignment, and it kills me to rush this because this is something I'd really like you to understand more deeply, but I got to show this to you fast. Let's take a look at exponential equations. Like, what about that? And what I mean by that is, what you now understand is if x is raised to any number, you're good to go. I don't care if the number is negative, positive, fraction. But what if the original function was an exponential equation? What does it mean to be an exponential equation? And let's just use e as the base for now, but you know, what if it was that? So what's in the exponent now? It's not even a number, it's a letter. And so you might wonder, is it the same? In other words, you bring the x down front and It looks like that. Does that make sense? That'd be the power rule. And if that was true, I wouldn't be surprised. Unfortunately, the answer to that is like it doesn't work. So the power rule works. I guess you might go back and say the power rule turns out to only work. And again, we're rushing this too fast. Actually, I'll use some language for you. N is in the set of the real numbers. N's a number. N has to be a number. It can't be a letter. It can't be X. It doesn't work. Maybe we'll have time on Monday to talk about this in a little more detail, because me just telling you it doesn't work is not very good pedagogy for teaching. It's kind of like, what I'd like to do is graph that and kind of look at the two graphs and go, well, that isn't apparently right. Watch this. Well, that doesn't work. Well, would you agree that the definition of a derivative would say that the derivative of e to the x is, well, e to the x plus h minus e to the x all over h as h goes to 0? Isn't that the definition of what a derivative is? Like, we sort of can't cheat here, because we're looking to cheat now. We're looking to use this cool shortcut and not have to write derivatives out like this anymore. Get your graphing calculator warmed up. Get your fingers warmed up. I got to show you something here. So that's the shortcut doesn't work. So we have to go back to the original definition of a derivative. How's your algebra skills? E to the x plus h. Hey, didn't we just say that you add exponents a minute ago? Right there, x to the first times x to the 1/2, you add the exponents. That's a shortcut. So would you agree here that e to the x plus h would be e to the x times e to the h? You agree with that? And then I could say, well, I guess this minus sign here, there's two e to the x terms, so I guess I could take the e to the x outside in front, and then that would leave e to the h minus 1 over h. I'm just doing algebra. Again, I'm guessing for some of you, it's like, oh crap, I don't remember all these exponent rules, and like, take your time, go back and look at this. And again, we are looking at this as the limit as h goes to 0. What I want you to stop and consider, and this is why mathematicians spend time with the concept of limits and why chapter 2 exists. But if I had bored you for an extra week with chapter 2, you wouldn't understand where this is going. But that's what I want to ask you now is, what happens to e to the h minus 1 over h as h goes to 0? Well, if you put in h is 0 now, do you see that it breaks? It's broken. What's e to the 0? E to the 0 is 1. 1 minus 1 is 0. So you have 0 on top, 0 on the bottom. It explodes. Doesn't work. But this one is not simple. I want you to cheat on your calculator and try h is 0.01 or perhaps 0.001. And I want you to tell me what the limit of that is. I want you to tell me what happens to e to the h minus 1 over h as h gets really close to 0. As you may not be surprised, you don't get, like it explodes. Somebody tell us, what is e to the 0.01 minus 1 over 0.01? And what is e to the 0.001 minus 1 over 0.001? What do you get?
I got negative 998.99. Did I do that right?
No. See if you can figure out why. You got to be careful how you type this into the calculator, because notice everything on top is divided by 0.01, not just the bottom number. Therefore, to type this in your calculator, you're going to have parentheses there.
I got 1.0050.
1.0050.
And I got 1.00050.
For the second one?
Yeah.
What does it appear that statement, that part of our answer, what does it appear that that part of our answer then is on its way to as h goes to 0?
1.
It appears that it's on its way to 1. Now, again, we're not proving this. A real mathematician would say, how do you know it's on its way to 1? Like, we got to prove that somehow. I'll talk about that later once you understand derivatives a little better. What we're actually saying here then is copy, paste. We're actually saying then that, amazingly, this portion of it is on its way to 1. So if the original f of x was equal to e to the x, then what does that mean the derivative is? What's the derivative of e to the x?
1.
Notice this part of it went to 1, but that's still left behind. Right?
So it's the derivative e to the x then?
The derivative of e to the x is actually e to the x. What? Like, this is an equation where the y values are the derivatives. What are you talking about? We got a second here. I got to go fast, but we got a second. If I say that f of x is equal to, and again, amazingly, your calculator understands that e is 2 point. Remember, e is just a number. Don't forget that for your assignment. E is not a letter. It's 2.718. What is, if I make a quick, I got to do this fast. I hate to rush something so cool. This is just criminal what we are doing here. I'm making a slider again for this. And so we cruise along, and let's add that label. And so let's say we're sitting there at x is 2. That's not a 2. At x is 2. So the y coordinate is 7.38. What would you say the slope is right there? What's the slope right there? You're guessing. What kind of a number?
7, 8.
Maybe 7 or 8, somewhere in there, maybe 10, maybe 5, something like this. Let's cheat and see what does the actual answer, what is the actual answer of this? What's f prime of a? What do you notice?
The slope is the y value.
This is the only equation where the y coordinate of the equation actually is also the slope of the equation. Let's move along. Down there, the slope is pretty small, right? It says it's about 0.741. What's the actual slope? 0.741. You see what I'm saying? Like, the derivative of e to the x is e to the x. This is one of the weirdest equations that exists. So it is not, my point is, let's just, I want to put this in the notes. I gotta shut up. I realize that. The y coordinate is the slope. Isn't that the weirdest thing? The y coordinate of this is the slope. I'm gonna take a picture of this. I'll be done in 30 seconds. Oh, that was not correct. That's not where I want to be. I want to be right there. Paste this into the notes. Yes, add it in there. Crop that thing down so that we can see only what we need to see. Good, make it larger so we can see it. Do you see that that seems to be true? That the derivative of e to the x is e to the x? That's just really weird. Remember, our hypothesis back here was maybe the power rule. So it was kind of like, power rule? What is the derivative of e to the x, x times e to the x minus 1? Apparently the answer to that's no. It's actually simpler than that. So power rule only works where the exponent is a constant. If the exponent is a letter, it's a little more complicated. We'll see this come up a little bit later, but you have some questions in your assignment where e is involved. And so e is the best thing ever to take the derivative of, because you don't have to do anything. That's really cool. All right, I gotta shut up. It's way over time. But again, as usual, you're more than welcome to stay after and ask me questions, but I just want to make sure you can leave if you want to leave. You know everything you need to know to do the assignment, but you're probably going to need to look back at my notes a little bit and, you know, think this over. I'm sort of disappointed today is a Thursday because you have to do your assignment. I'd love to kind of kick off tomorrow with a little bit of discussion. This is an amazing day, an amazing day. Like, wow, there's a shortcut to this. I can't believe it. It's amazing how much we can do now with like very little work. But this class devolves into, let's take the derivative of everything using shortcuts. And you're going to kind of forget that the derivative is a slope because we're using the shortcut now to answer these questions. And the fact that it came from f of x plus h minus f of x over h is kind of lost now. Like we're not having to use that anymore because we found shortcuts to this stuff. And that's what this class will devolve into, is now we say, oh, what's the derivative of sine? What's the derivative of natural log? What's the derivative of exponential equations? And we kind of started the exponential discussion today. And so the shortcuts are not always the same. Power rule is one rule, and now there's kind of a second one here, and that's like how to handle e to the x. But we're going to go on and look at what's the derivative of sine, and what's the derivative of tangent, and what's the derivative of natural log of x, and things of that nature. The derivative of e to the x is e to the x, but what's the derivative of 2 to the x? Is the derivative of 2 to the x 2 to the x, or is it different? These are questions that we gotta answer. So enough said. See you Monday, my friends.
I have 2 homework questions because I'm special. Question 5 and question 6 from 3.1. 3.1 is killing me.
Nice.
It's like, it's killing me slowly. And
Killing me softly.
It's obliterating my soul.
Your soul, I love that. I told you already that my single goal is that this class would ruin your life, and it sounds like it's already happening.
Look, it's like I understand the concepts you're teaching, but then like the way the homework asks them sometimes is just like so far-fetched from what we're talking about in class. I'm not.
And I will apologize for something, which is I'm teaching for conceptual understanding, and so I'm using words like badass and junk, and like you're not going to see those words in a math book, right? And so you find yourself understanding what I'm saying because I'm speaking English. But in a sense, I'm doing you a little bit of a disservice because I'm not always speaking the language fully correctly. And so sometimes you'll read in a question that somebody wrote, and it'll be like, I know what Doug explained in class, but I don't understand what this question's asking. And that's a part of this. I don't regret the way that I do this, but in the end, for you to say, what is this question asking? And then I say, this is all this is really saying. And then you go, okay, I understand that now. That's a then negative to the style in which I teach this. If I speak really formally, then you don't understand what I'm talking about, but you can do the assignment, but you're just doing it by memorization. It doesn't make any sense. If I speak English to you, then you understand the concepts, but then if you read it in a textbook where people speak formally, because you can't use a word like junk in a math book, right? So that's the rub, and that's what I expect. Is I expect you to stay after class and ask me like, what is that asking us to do? So having said that, tell me one of the questions. What's it saying? And let's write part of it out, and then we'll talk about it.
All right, so it's question 5 and 6. Those 2 are screwing with me. So question 5 is the population of a slowly growing bacterial colony after T hours is given by P is a function of T equals 3T squared plus 26T plus 100. And then I need to find the growth rate after 4 hours.
Yeah, wonderful question. So it's not F's and X's, it's P's and T's. And so as time changes, the population changes. And that makes sense. And because this is 3T squared, I know it's a parabola, and I know it's facing up. And so we're talking about a population that as time goes by, the population drops to a minimum, and then it goes back up again. I can see that happening with a population. And so the important question was what? Find what?
Find the growth rate after 4 hours.
Find the growth rate. Growth rate, rate of change is code for derivative. Growth rate is how is the population changing? Not what is the population, The original question allows you to answer questions like, what's the population at hour 7? What's the population at hour 10? But there's a second set of questions that somebody might want to know the answer to, which is, how is the population changing? What's the growth rate? That's code for derivative. That's code for slope. That's code for rate of change. Those are all synonyms. Slope, rate of change, derivative, all mean the same thing. And then because of today, and you couldn't do this, and you had to do this the long way in 3.1, but because of today, you should be able to say, oh, 3t squared, I know what the derivative of 3t squared is 6t. I know what the derivative of 26t is, it's 26. And so if you say, what's p prime of 2, the number you're getting out of that, 12 plus 26, is 38. What does that mean? That means that since, and remember this is a slope, it's 38 over 1. And since the top was y minus y, which is p was population, and on the bottom 1 was hours. And so this is an increase of 38 people in 1 hour. When 1 hour goes by, at hour 2, when 1 hour goes by, the population is actually going up by 38 people, or 38 bacteria, or 38 skunks, or whatever population you're talking about.
Okay. I guess it makes more sense when you put it like, I'm a dumb mechanic. So I needed it in dumb mechanic terms.
You dumb wrench turner, get over here. I'm actually disappointed we didn't have time to answer this during class, because you're not the only person that, like, I really want this to make sense to you and for you to see why derivatives are so cool. I mean,
so
it's wonderful to find the slope of an equation. That's all we did today, but it's like to apply this to something is where it's really beautiful.
So basically anywhere it says, like, say it says solve like f prime of 2, is that basically saying solve the derivative and then plug 2 into x, right?
Yep.
Okay, that's what I thought, but I wasn't sure. So then going forward on question 6 is, I struggle with the slope where you have to give the equation of the line. That's one of the things that I'm struggling with right now. So it's x cubed minus 8x plus 8 is the equation for f of x. And then it says compute f prime of -1, which is fairly easy to do with this equation.
Correct.
Because that would just be what it'd be, 3x squared minus 8.
Right.
Yeah. For f prime of 1, for f prime of x. And so -1 would be what? It would be 5 for f prime of 1. Because -1, or no, it'd be -5,
Right.
my bad.
3 minus 8, which is -5. That's what you said. That's exactly right.
So then from there, -5 is my slope, right?
-5 is your slope.
For f prime of -1.
Yep.
So then, but this says find the equation of the tangent line for the graph of f of x at -1, 15.
Yeah. So it's not enough just to stop at the slope at that point. So it's like, it's kind of like you're sitting over here and you're saying, what's the slope right there? Oh, it's -5. Okay, great.
So, and then it gives me,
Like you're done. But this problem is saying, no, go one step further and find the equation of that tangent line on the curve right there.
yeah, and it says find the equation of the tangent line graph of f of x at the point -1, 15. And this is the part that's throwing me off, is like I got the f prime of 1, I got that, but then it gives me this other point with f of x, and I'm not sure how to give you a tangent line there.
So in order to know the equation of that tangent line, you got to know the slope of the line. So if you know the slope of the line, don't you already know the equation is y equals -5x plus something, because the slope is -5, right?
Oh, okay. Yeah. Okay. I see what you're saying. So then you just go, your y value is 15 because it gives it to you right here at the point -1, 15.
Right.
So then you go, what, -5 times -1 is what? 5. So 15. So it'd be 10. So it'd be y equals -5x plus 10.
Exactly. Now go graph all that and make sure it looks right. Make sure it looks tangent. Like you could screw anything up there. You could get the slope wrong. You could get plugged point -1, 15 wrong. If there's all kinds of math mistakes you could have made, but it's like, go graph it. There's a visual representation of everything you just did.
Gotcha.
Yeah.
All right, so one more question.
Go
I
ahead.
promise I'm not trying to be a pain in the butt.
This is no fun to me if you don't get it. Like, I'm not just teaching to hear myself talk. I already know this stuff. If you
So
don't get it, it's no fun to me. So
yeah, so there's f of x equals 6 over x. That's my base equation. So I mean, this is I think I got this now because we have the sweep power rule, which makes this way easier. Which then so f prime of x would then be well, f of x basically equals 6x to the negative 1. So that would be negative 6x to the negative 2.
exactly right. But you should be able to, and I'm going to ask you this on a test. In 3.1, you should be able to say, this is f of x plus h.
Yeah.
There's f of x with x plus h in it, minus f of x all over the top of h as h goes to 0. You should be able to produce your
Yeah.
from today. We know the answer to this is negative 6x to the negative 2. You should be able to get this to produce that same exact answer. Like, that's the slow way, and it still works. It's just a cool shortcut now.
So, and this one is just an LCD problem, effectively, right? X times x plus h is what you're going to multiply top and bottom by, and then you'll cancel everything out, which we did earlier.
Yeah, go back and study that. Like, study the algebra of it. Take your time and make sense of it. I forgot where we did that, but I think it was right. We're getting close. It was right here.
Yeah.
We did that problem the long way, and then we noticed, oh my God, the power works for that too. But like,
but we can still do it with the equation to solve.
Yeah.
The long way for 3.1.
And you're like, I'm just a dumb mechanic, but that, like, you should have to go back over your algebra knowledge here. I did it one time, 1 year ago, 2 years ago, 5 years ago, and I even got an A. Is not the same as actually understand it and have it on board today.
Why can't you see him?
So you should be having to scratch your head over this stuff.
Yeah, I think I see what I'm doing wrong now after this.
Teacher, I couldn't see it.
Love it.
Teacher.
All right, I gotta get off here and figure out what's going on with my kid because he's yelling at his iPad.
I couldn't see it.
Adrian, you got anything you want to?
Yeah, I was gonna see what exactly assignments are due. I got the My Open Math, but is there like paper assignments we have to do, or?
Yes, but those aren't due. Those aren't due today. If you go into, I'm sharing a screen with you really quick right now. If you go into My Open Math and you go into chapter 3, well, and you can look at the calendar and see this too, but really we went over 3.3 today. So for Sunday night, you owe me 3.1, 3.2, and 3.3. That's what we covered this week. But then there's also this quiz up here on top.
Okay.
But on the syllabus, that isn't due for a long time because it's got questions from 3.1, 3.2, 3.3, 3.5, everything. See how it goes from 3.1 all the way to 3.6?
Yes.
So you don't owe me that for a long time. If you go back and look at the calendar, it shows right here, you don't owe me that quiz until Monday the 12th, which is a week and a half away. And so these three are the ones you're going to owe me. If I click on those, I think I can click on them. You owe me.
That's just the grade book ones.
Yeah, that's just the regular grade book ones.
So the quiz we can start on now, and then it's not owed till the 12th.
Yeah, and you should be working on it the whole time. Don't save it for the next night because we're like, for instance, I taught you 3.3 today, and there are some three questions that are really like, those are the big takeaways from this section. And so I begin to work on those, so it isn't like a big pile of work on the night of the 11th, but also so that you're making sense of the power rule.
Okay. And then, so we can keep signing into that one. If you go onto the one on My Open Math and click in and start it, you can sign out and sign in to the test.
Yeah, you don't have to do it like all in one sitting. You can do a few questions.
Okay. Well, that's it.
Okay.
Are you gonna submit like chapter reviews before each test too that are non-graded?
The chapter reviews are just there for you to study for the test. They're not graded. I'm not grading them. There's a
Gotcha.
blank one, and then there's my solutions. So it's really just in there so that you can practice and then look at my solutions and see if you got the right answer. And then if you didn't, you can look at what I did and go, oh, okay, I see
Gotcha.
what you did. Yeah, I screwed that up. You know, they'll be
I like having those because on the day of the test, I like to like go through the chapter review and refresh the whole chapter in my mind before the test.
yeah.
It's always a good tool for me.
Because it's one thing to understand math a day at a time. It's another thing to put all the pieces together. I mean, it's like basketball. You know how to dribble, you know how to do a lay-in, but it's like, okay, now you're in the game. Can you dribble and do a lay-in at the same time? Can you pass it behind your back to somebody? Like, you got to be able to put it all together to play basketball. And that's why I think it's important to have a review, because it's like, have you actually put it all together? That's a way for you to see if the answer to that is yes or if it's no. Ideally, I don't like tests to be memorization related. I think that's a part of it when you're first learning, in a sense. Maybe there's no way to avoid that completely, but one of the things I stuck in, I got to remember to show you guys this.
Well, and I think the other important thing too is like as we're moving forward, we're coming up with shortcuts, and these shortcuts we're probably going to lean towards more than the harder way to do it. Before, so like especially in this chapter, where like in 3.1, you're going to ask us, hey, do this with this equation, where don't use the shortcut. So then like if I like say we've moved on, I've forgotten that equation because I have this convenient shortcut.
Mm-hmm.
Well, it's good to, for me at least, it's good to go back and review that stuff so I can still do it the long way.
You guys help me remember to show you guys this on Monday, but I just went into course information. So you're usually just working down here, but there's class notes that I'm posting every day. But back in course information from the very start, I posted something called Calculus 251 Notes. This is what you have available on the test. And so we're actually into it now. Can you stare at these first two items, the definition of a derivative, definition 1, definition 2? Do you find yourself going, oh yeah, thanks for reminding me if I'm taking a test as to what definition 2 is? And then today I just taught you the power rule. Like, can you look at that and go, if y is x to the n, then y prime would be n times x to the n minus 1. Is that a good reminder to you of what the power rule is? And notice there's other rules coming: product rule, quotient rule, train rule. There's other rules coming, but this is like everything you need to know for this class, and I'm slowly going to reveal it to you. By the time we get to that first test, you're going to be halfway through this list of cool shortcuts. So this is why you don't need to memorize stuff. So this is like a quick one-page cheat sheet of everything we're going to learn this entire term.
Annie had one of those for us for 112. It was super nice. Had like the unit circle and everything on it, and she let us use it.
Yeah, there's the trigs. There's trig ones in there too that printed out. I saw.
Yep.
You remember?
We've got to get to the place where we say, what's the derivative of sine? And the answer to that is cosine, but it's like, you should look at that and go, what? Why is that? We'll get to that later on.
I think one of my favorite things about MyOpenMath is you can go back into your previous classes and like get information from there.
Yeah, I completely agree. It's like you can go replay with stuff that you knew at one time when it was fresh, but now it's not so fresh. And teachers will never tell you this, but unless you've taught a class like 6 times, you have to go back to. I have to go back to, if you will, when it's something I've just recently taught. I don't have to do it with calculus because I've taught calculus like 20 times now, but.
All right. Well, thank you, Greg. I'm going to go get this 3.1 assignment finally finished.
All right. Thank you. Take care. Have a good weekend.